Dear student, welcome to my channel. Topic of this video is linear regression by gradient descent approach. Now let us start. Gradient descent approach. Linear regression by GD is a method used to find the best fit line for a set of data points by minimizing the error between predicted and actual values. The concept behind GD is to iteratively adjust the parameters, that is nothing but slopes and intercept of the line, to reduce this error. Starting from an initial guess, the algorithm calculates the gradient of the cost function and updates the parameter in the opposite direction of the gradient. This process is repeated until the cost reaches a minimum, ideally resulting in a line that best represents the data. Machine learning occurs here as the model learns the optimal parameters through repeated adjustments and improving its accuracy with each iteration based on the feedback from the cost function. In the context of machine learning, especially when applying algorithms, the following key components plays a crucial role. First is data, second is model, third is parameter, fourth is algorithm, and fifth is objective function. Now we will see for the gradient descent linear regression what are these important parameters. Data. It consists of the input features and corresponding output labels, that is nothing but data set, which is used to train the model. It provides the foundation upon which the model learns patterns and relationship. Example, in predicting the house of prices, the features might include square footage, number of bedrooms, and the location, while the output label is the actual price of the house. Now we will see the second component, that is nothing but model. A model defines the mathematical relationship between input features and output prediction. It serves as blueprint that maps input to output based on the learned parameters. For example, in linear regression, the model is typically represented as, that is, y cap is equal to beta 0 plus beta 1 x1 plus beta 2 x2 dash 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 up to beta n xn. This is equation for multiple linear regression. For simple linear regression, only one slope intercept and one slope will come. Third is the parameter. The parameters are the coefficients that are adjusted during training to minimize the prediction error. It defines the specific form of the model, enabling it to fit the data accurately. And the main aim of machine learning is to learn this parameter to find their optimal value so that the error will be minimized or maybe maximized depending on the situation. So here in this equation of linear regression, so beta 0, beta 1, beta 2 up to beta n, these are nothing but the parameters of the model. Fourth is the algorithm. An algorithm is the procedure used to optimize the model parameters based on the data. It guides the learning process, ensuring that model converges to the best possible parameters. For example, gradient descent is an iterative optimization algorithm that adjusts the parameter in the direction that reduces the cost function. Fifth is the objective function. This objective function quantifies the error between model prediction and the actual data. It provides a metric to evaluate how well the model is performing and guiding the optimization algorithm to improve the accuracy. In linear regression, we are using mean squared error is a common objective function. So this is the formula for mean squared error. Mean indicates that is nothing but the average. So it is total n samples are there. So 1 by n, summation 1 to n yi minus y cap square. So here yi is nothing but the actual value and y cap or y hat is nothing but the predicted value. So we require to minimize this difference. So when we are minimizing the difference by adjusting the parameter, and that adjusting parameter is guided by the gradient descent. Linear regression with gradient descent algorithm steps. Data. Collect input features and corresponding output labels. Choose a linear model to represent the relationship between features and output. Parameters. Initialize the coefficient of the linear model. In algorithm, we compute the gradient of the objective function with respect to each parameter. updates the parameter in the opposite direction of the gradient to minimize the cost. So with example it would clear why we are going in the opposite direction of the gradient. Repeat until convergence when changes become negligible. Objective function continuously evaluates the error to ensure that model is improving. Now before going for the linear regression equation, we will see the equation which is having only one parameter, that is nothing but x. Now see, the equation is f of x is equal to x square minus 2x plus 7. When we plot this equation on the graph, then we are getting this convex shape, and here we can see that this is the global minima for this function. So this is x-axis. So when x is 1, this function have a value of 6. So this function has minimum value 6 when the value of x is 1. So the same for the parameters of the linear regression, that is nothing but beta 0, beta 1, beta 2 dash dash dash. So we require to find out the minimum value, and this function for linear regression is minimization function, because every time we are reducing the error between the predicted value and the actual value. So the function is of minimization, and that function have a convex shape like this function represented by f of x. Now here we can see that when we are getting the minimum value when x is equal to 1, and that minimum value is 6. Now we can see that this shape and like this. Now here we can correlate it with that. For example, in a line, this is a negative slope and this indicates a positive slope. So here we can see that this gradient is moving this side, and here the gradient is negative, and this side the gradient is positive. So when gradient is negative, we are moving to the positive side of the x. So for example, we are moving from -5, -4, -3, -2, because our target is to reach 1. So and when the gradient is positive, at that time we are moving in the opposite direction, that is nothing but we are decrementing. So from 5 we are decrementing 4, 3, 2, 1 in this way. So that's why we are moving opposite to the direction of the gradient. Now see this equation. Here we can either start with the minus value or positive minus value or plus value. So for example, see, the minimum function or optimal value is when x equal to 1, at that time value is 6. So either you can start with -4 or you can start with the +4, but our final aim is to reach this value. So when -4 is there, we are getting the 31. So to reduce the loss, so because our actual value is 6, and we predicted initially value 31, so loss is more. So gradient descent algorithm guides us to mean a proper direction. So according to the opposite direction of the gradient, we are moving to the -3. So -3, then our cost predicted value will be 22. So 22, 6, again difference is there. So again we will decrement this value, loss is decreases. So when x becomes 1, at that time we are getting the 6 value. At that time there is a zero difference between the actual value and predicted value. And similarly, if we start with the 4, so at every step we are moving from 4, 3, 2, 1. That is, here we are decrementing the value and here we are incrementing the value. So it is all depends on the slope of the gradient, and we move always in the opposite direction of the gradient. Minimization function. Each point on this curve corresponds to the particular choice of parameters with the highest representing the error. By moving downhill, that is nothing but the minimized cost function, we aim to reach the lowest point or the global minima, which represents the optimal parameter that yields smallest errors and best possible fit. Because this function shape is convex, and here we have the actual answer, and here the derivative at this point is 0. So our aim is to find out the derivative and equate that derivative is equal to 0, and we will get directly solution. But every time the equations are not simple like this, so we can't directly take the derivative of the function and make equate to the 0 and calculate the answer. So the gradient provides a direct path to the solution. See, this is the function f of x. If we take the derivative with respect to x, it will give 2x minus 2. At this point derivative is constant, so that is nothing but 0. So equate derivative to the 0, so 2x minus 2 and x equal to 1, and we will getting the direct solution with the help of derivative. and when x equal to 1 we are getting our solution. But in real life every time this equation is not simple, so here we are learning the parameters. So here we are learning the x value, so either we will start with any value positive or negative, and iteratively we reach to at this location. This equation is very easy and with only one parameter, but in practical situation more parameters are there and we can't calculate directly. We need to learn the parameter value such that derivative is 0. With gradient descent we don't know what is the value of optimal value for x, therefore we pick a random number. So that's why either we can start from this side or we can start from this side. So now we start from x equal to 3. So when x equal to 3, at that time we always not work with the original function but we always work with the gradient. So gradient of this function is 2x minus 2. So we will check 2 plus 3, we start with the 3. So 2 into 3 minus 2, we are getting the 2. So if this answer is 0, we stop there. But here the answer is not 0, that's why we require to iterate. So from 4 we are going to the from 3 we are going to the 2 1 0 in this way. And if we start with the opposite direction, that is x equal to minus 3, at that time the value is minus 8. So that means here derivative again is not 0, so we are going in the opposite direction, so we will go to minus 2 1 0. So either we start with the 3 or minus 3, eventually we will reach to this particular point. Either we will start from this side or either from this side, gradient descent automatically comes in this direction and here we will get. So here when we are moving from this point to this point, at that time we are not directly going but we are making step by step approach, and that is indicated by learning parameter alpha. So here also we are not going directly from this to this. It is possible only when the equation is very simple like this, but in reality the equations are not that much simple and even the objective functions are not that much simple. Therefore we require to take the step by step approach to move from this point to this point or from this point to this point. When we apply the gradient descent algorithm, we can start at any point and GD will guide us to reach a global minima, that is a point where derivative is 0. Gradient descent equation, this is the important equation. So the equation is x of I plus 1 is equal to xi minus alpha f dash of x. Now this x is nothing but the parameter and this is old value, that is current value, and this is a modified value. Alpha is learning parameter, so alpha determine what steps we are taking towards a solution, and this is nothing but derivative. And in this way we are updating the value. So we can start with any random value of x, which is maybe either 3 or minus 3. It will reach this value to 1 where we get the minimum solution. So this is the basic equation. Now for linear regression, instead of x our parameter will come, that is nothing but beta 0, beta 1, beta 2 up to dash dash dash. Now see here learning parameter is given, that is 0.2. This is only for the explanation. So here our actual answer is 6. So initially we start with the 3. So from 3 we are getting the modified value as 2.20. So we will check this, we will put this value into this. So our answer should get the 6 value, but here we are getting the value of 7.44. So still loss is there because actual value is 6 and predicted value is 7.44. So again we are moving. So from 2.20 we are again getting new x of I, and in this way we are doing, and when it gets a value modified value 1, and when we put this value into the equation, so at that time we are getting the value as a 6, and we can say that our error between the actual and predicted value is 0. So that is a stop, and here we stop when our error function is getting 0 value, that is there is no difference between the actual and predicted and the error is 0. So either way we start with the minus 3 also, and here we are updating the value of each x and we are putting into the equation, and when our answer gets close to 6, then at that time we stop the procedure. And at this point, when we are getting this point is 1 and this point is nothing but the solution point, and we have already seen that in this equation when we put 1 directly, because this function is very simple, our solution lie when our x is equal to 1. So with the gradient descent, we are making the step-by-step solution towards the final global minima. So this is the function. So here it is three-dimensional because both parameters are showing for the simple linear regression beta 0, beta 1, and this is nothing but the mean square error. And we can see that this function is of minimization. So for one dimension, for separate parameters, the function can be represented in two-dimensional figure, and we can see that the function is of convex shape, and here our solution lies. That is the optimal value for beta 0, beta 1 when our error is minimum or close to 0. So this is nothing but the mean squared error, and this is with respect to beta 0 and beta 1. Now here, as we are not making directly jump from here to here, so we are making the step-by-step solution. So that is indicated by learning rate, that is, this is hyperparameter, and that is nothing but alpha. The learning rate controls the size of the steps taken in each iteration to minimize the cost function. If alpha is too small, the gradient descent will take very small steps towards the minimum and making the process slow and inefficient, and for convergence also it takes more number of iteration. If alpha is too large, gradient descent may take steps that are too big and potentially overshooting the minimum. A large learning rate can cause the algorithm to fail, converge, or even diverge, meaning it moves further away from the minimum instead of closer. So I will explain with this example. A moderate well chosen alpha balances efficiency and stability and allowing gradient descent to converge effectively to the minimum. Now see, this is the solution lie, that is optimal solution. So if we take a very small step, so at that time more number of iterations are required to come here, and if we take more that is the drastic step when alpha is large, so at that time it may happen that at this point it will not come to here but it will reach here, and again it is moving away from the solution. So that's why we require to choose that alpha hyperparameter in such a way that we will get the convergence. So here if we choose alpha very small, more number of steps are required to reach here, and if we take alpha very large, at that time it may happen that we come to close to solution, but after that we immediately switch to the another position which is away from the solution. So that's why this is a simple example, so that's why we get the convergence. But if I increase the alpha rate, it may happen that we are not getting the solution and we are just back forth between this particular position, that is the negative slope and positive slope. Now this is the basic equation. Now here only difference is that here we require to switch from x to beta, and this is nothing but our mean squared error function. Modify this basic equation of the gradient descent for linear regression with two parameters. So first I will explain for simple linear regression. Our aim is to find out the optimal value for beta 0, beta 1, which minimize the loss between the actual value and predicted value. And here our cost function, that is f of x, is nothing but our cost function, and we are taking the derivative of that cost function because the derivative gives the fastest path to the solution. So equation become beta I plus 1 is equal to beta I minus alpha. This is learning rate, and this is our cost function which is indicated by j, and this is the function of with respect to parameter beta I. For beta 0 we can say that beta 0 I plus 1, this is nothing but the modified value or updated value, beta 0 I minus, here two parameters are involved, that is beta 0, beta 1. For simple linear regression, so we require to take the partial derivative. So instead of this equation I am using this equation because this is easy to remember and understand, that is updated and this is old value, minus alpha partial derivative with respect to beta, and similarly equation we can write for the beta 1. So for multiple linear regression only change is that for beta 0, beta 1, beta 2, for example 3 independent variables are there, then we require to write down the equation for beta 0, beta 1, beta 2, beta 3. So there is as such no difference between the simple linear regression and multiple linear regression when we use the gradient descent approach, because here only we require to learn more number of parameters, and this is the advantage of machine learning, that once we learn the basic algorithm, even we can extend it for the more number of parameters. Cost function is mean squared error, which is given by 1 by n summation 1 to n yi minus y cap square. Then here y cap is nothing but beta 0 plus beta 1 xi. This is our basic equation, because here y cap we are learning the parameters, that is nothing but beta 0 plus beta 1. So here we require to take the derivative of this function. So we are taking the derivative. So derivative with respect to, so this is our basic equation. Now for I will take with the first beta 0. So here this function is very simple, so we are taking the derivative with respect to beta 0, and here we are taking the derivative with respect to beta 1. So I have just represented the equation again to understand clearly. Now see this derivative. Here the parameter is beta 0 beta 1, x and y are not the parameters. So here yi is always constant because that is nothing but the actual value, and xi is nothing but associated with each record, and even yi is again associated with each record, but they are not the parameters. The parameters are beta 0 beta 1. So when you take the partial derivative, it becomes 2 by n, and here for beta 0 it will multiplied by -1. So this is the final equation, just adjusted with the minus term. And similarly equation comes for the beta 1, only we require to multiply with the xi. So this is the equation, and here as this minus beta 0 and minus beta 1 xi comes, that's why we are multiplying with the minus xi. After adjusting the parameter, this plus minus sign, we are getting this final equation. So as this function is convex or ball shaped, it has only one global minima, so we never stuck up in a local minima. So it gives a convergence, and we get the optimal value for beta 0 and beta 1. Now sometimes when we are implementing, at that time for simplicity we are not using 2 by n, but initially equation of that mean square error we are taking the 1 by 2n parameter, but it does not make the difference because we are controlling this equation by the alpha parameter. So thereby we can use either mean square equation as 1 by 2n or 1 by n. It does not make any difference. The constant 1 by 2n is a scalar factor that does not affect the direction of the gradient but only its magnitude. Gradient descent only requires the direction of the steepest descent and not the exact magnitude of the gradient. Therefore this constant can be ignored to simplify the calculation, and basically we are controlling this equation by the alpha parameter. That's why either we can use for the mean squared error 1 by 2n or 1 by n. Now when we implemented practically, at that time I have taken only 2 samples, that is 1, 2, and that 2, 4 values are there, and initially we start with the any values, but here I have just given we start with beta 0 0 and beta 1 1, alpha is equal to 0.1. So we just require to iterate this algorithm until convergence takes place, that is the value between the y and y cap is close to 0 or less than particular very small value, and every time we are updating this beta 0 beta 1, and once we update we again calculate the y cap and take the difference between y cap and y. If that difference is 0 we stop, otherwise we continue the parameter updation of beta 0 beta 1. So in this way we get the updated value for the beta 0 beta 1. Multiple linear regression with gradient descent. In gradient descent, the approach for optimizing parameters in simple linear regression can be extended to multiple linear regression by only adding more parameters corresponding to the additional features, but the core process, that is nothing but calculating the gradients and updating the parameters, remains the same. Real machine learning takes place as the model iteratively adjusts these parameters to minimize the error between the predicted and actual value, and learning the relationship between features and target variable. So for multiple linear regression, only our y cap equation is like this. Even for y also, that number of independent variables are there, so only we require to update the parameters depending our total number of independent values of x. So if 3 independent variables are there, we are updating beta 0, beta 1, beta 2 and beta 3. So that is the advantage of gradient descent, that once we write the program for a simple linear regression, it can be easily extended for the multiple linear regression. So that is all about the linear regression with gradient descent approach for simple linear regression and multiple linear regression. Thank you.